Okay, hello class. Today we're going to be talking about infinite sets and their cardinalities. Just a refresher, cardinalities, the cardinality of a set refers to the number of unique elements within that set. Now, one idea that's going to be very important today is this idea of a one-to-one correspondence. So go ahead and copy this down. Two sets have a one-to-one correspondent if each element from the first set can be paired up with exactly one element from the second set. So what this means, let me zoom in here. I tend to think of a one-to-one correspondence kind of like speed dating. Ideally, I've never been speed dating, but I hear, well, I don't know. I like to think of it as speed dating. So you have two sets. And I guess the hope of speed dating is that you will go and in a quick and efficient manner you will meet your soulmate or something like that. And if everybody who shows up for speed dating finds somebody who they believe is their soulmate, and this person thinks that the other person is also their soulmate, then these two are a pair. These two go together, these two go together, and these two go together. If every single person from one set finds a partner in the other set, and it's exactly one partner, then we have a one-to-one correspondence. We do not have a one-to-one correspondence if we have these two people who think that they're soulmates, right? They're happy with each other. But then we have 9 who's like, oh yeah, you're my soulmate number 3 and you're my soulmate number 7. That doesn't work, right? Because it's not one-to-one. Here we have 9 that's trying to, court 3 and 7. If we stick with this analogy of one-to-one and speed dating, which is so great for math, right? Okay. So one-to-one correspondence, every element in one set can be paired up with exactly one element from the other set. None of this double dipping here. All right. Let's talk about equivalent sets. Two sets are equivalent if you can put them in a one-to-one correspondence. So suppose we have set A is the set 2, 3, 7, and set B is the set 5, 9, 10. Because I can put them in a one-to-one correspondence, we can say that these two sets are equivalent, and we can notate it like this. Please note, though, equivalent does not mean equal. Remember, equal sets are where every element in A is also an element of B, and every element of B is also an element of A. They share the same elements. Here, we're just trying to create a one-to-one correspondence, and we say that they are equivalent, if we can. Now let's talk about the cardinal number aleph naught, also known as aleph null. If you, whoa, wrong direction, crazy. Okay, if we want to, sorry, my Zoom function here is kind of spazzing out a bit. There we go, we're back on track. So the cardinal number aleph naught, also known as aleph null, is this. If you want to get really geeky, you can get this tattoo, or I'm sorry, really awesome tattoo. This part is the aleph, and the fact that it has the 0 as a subscript, that's the not part of it, or the null part of it. And basically, aleph naught is the smallest cardinal number. Now, I'm going to write this as a squiggly capital N. That's what it's going to look like when I do it. Other people do different things. I'm going to do something along those lines. And we're going to say that aleph naught is the smallest infinite cardinal number. Aleph naught specifically refers to cardinality. It's not the same as saying infinity. So we're going to write a little note here. Aleph naught is different from infinity. When we talk about positive or negative infinity is used to represent the extreme values of the number line. So infinity, positive or negative infinity, are used to represent the extremes of the number line, and we use it like a number, right? It's a number, where aleph naught is specifically a cardinal number, and that's really the key here. And when we're doing this, when we're talking about the infinite cardinality of a set, there are different sizes of infinity. The smallest infinity is one where we can get there by counting. 1, 2, 3, 4, and so on. But there are denser sets that are not countable. And if they're not countable and they're denser, we can't say that they have the cardinal number aleph naught. They would have a larger cardinal number. So let's start talking about how we go about counting sets. And we're going to start with the set of whole numbers. The set of whole numbers begins with 0, 1, 2, 3, and so on. And what we want to do is we want to create a one-to-one correspondence between our counting numbers and our whole numbers. And our counting numbers are, if you remember this, the set of natural numbers. Which we notate with a capital N with a double bar on the diagonal. Ugh, my double bar is not working out. There we go. That'll do. So what I want to do is I want to write the set of natural numbers, and I want to show that I can create a one-to-one correspondence. So we're going to say 0 is the first number. This is my second number. This is my third number. This is my fourth number, and so on. And what we're doing is we are saying that the first whole number is this, 0. The second whole number is 1. The third whole number is 2. The fourth whole number is 3. And because I can count them, even out to the nth whole number, the number n is the n plus 1th counting number. If we look at this relationship, the whole numbers are 1 less than my counting numbers. And because I can create this one-to-one correspondence, we can say that the set of whole numbers is countable. Because I can count them, I can say that they have the cardinal number aleph naught. So let's talk about another set. Let's talk about the set of integers. And we're going to have to get creative for some of these sets. Now, the set of integers, which we can abbreviate with the capital Z that has a double bar on the diagonal. The set of integers is all negative whole numbers, positive whole numbers, and 0. So we start -3, -2, -1, 0, 1, 2, 3, and so on. Now I want to lay out my natural numbers. And I want to see if I can create a one-to-one correspondence. So if I write my natural numbers, that's 1, 2, 3, 4, we'll go 5, 6, 7, and so on. The problem I have is this. When I look at my set of integers, I don't have a first integer if I list it out this way, right? I can't go down to the very beginning of this list because this list goes all the way down to negative infinity. And it goes all the way up to positive infinity. So I can't say this is my first integer, this is my second integer. I'm going to have to reorganize it. And so what we're going to do is we're going to reorganize the integers in such a way that allows us to create this one-to-one correspondence. We're going to start in the middle. I'm going to start with 0. And I'm going to reorganize the set of integers starting with 0, and then I'm just going to bounce back and forth. I'm going to hit +1, -1, +2, -2, +3, -3. One of the things that's important here, one of the things that's important when you are trying to count a set is you need to have a systematic way of going through and making sure that you are hitting every single number possible. You can't skip anything. It can't be random. You can't say, I'm going to start from 0 and go on, and then when I'm done, come back around and do the negatives. You have to have a systematic way of making sure you are getting every single number with this method that we're creating. So we're starting at 0, going positive 1, negative 1, positive 2, negative 2, positive 3, negative 3. Now I look at this, and again, we're looking for this one-to-one correspondence. And I can see that my first integer, if I list it out this way, my first integer is 0. My second integer is 1. My third integer is negative 1. My fourth integer is 2. My fifth integer is negative 2. My sixth is 3. My seventh is negative 3, and so on. Well, what's a general relationship here? When I get to my nth integer, when I get to the integer n, positive n, what number is that? Well, let's look at the relationship between the positives and the counting numbers. I have 1, 2. I have 2 and 4. I have 3 and 6. I would have 4 and 8. So for the n integer, the counting number is going to be twice as much. For negative n, it's going to be the next number in the list, 2n plus 1. And I can continue this way forever. Now, because we have figured out a way to count every single integer, both positive and negative and 0, in a systematic method, and we can come up with some sort of general rule or a process to follow, we can say that the set of integers has the cardinal number aleph naught. And I don't think I wrote it up here. Can you guys fill this in as well? The set of whole numbers has the cardinal number aleph naught as well. Because we can count the whole numbers and we can count the integers. Go and flip your paper over. We're going to talk about the set of rationals. So remember, the set of rationals, those are any numbers that can be written as a fraction, a repeating decimal, or a terminating decimal. In fact, all repeating decimals and terminating decimals, all repeating decimals and terminating decimals can be represented as a fraction or a rational number. So the set of rationals is any number that can be written as some fraction a over b, where b is not 0, and a and b both belong to the set of integers. That's how we define the set of rationals. So we're really looking at all possible fractions. So what we have here is we have a systematic way of laying out all of the rational numbers. And what we're doing is we're saying, okay, I'm going to have these numerators, 1, 2, 3, 4, 5, 6, 7, 8, and so on. These are going to represent my numerators. And then we're going to have, along the blue, we're going to have this represent the denominators. And if I look at this list, what I have here, just cover this up. What I have here is every single fraction that has a numerator of 1. So my numerator is 1, denominator is 1. Numerator is 1, denominator is 2. Denominator is 3, denominator is 4, 5, 6, 7, 8, and so on. And in this row, I have every single fraction with a numerator of 1. Similarly, in this row, I have every single fraction with a numerator of 2 and all possible denominators. Now, if we go through in this way, we know that we're getting every single fraction possible. What we need to do, though, is we need to find a way of systematically counting them. Now, if I lay it out like this, I'm going to say that we start with the fraction 0 over 1. And if I start with 0 over 1, what I can do is I can start here, and then I'm going to come in and zigzag through this list. And I'll zigzag in pink. Okay, so I come in, and I'm going to zigzag through this grid. Now, because I've found a way to systematically list all of them, and we have a way to systematically get through all of them, we can say that this is countable. As we're going through, I have 0, 1 over 1, 2 over 1, 1 over 2, 1 over 3, and then I get to 2 over 2. This is a duplicate, so we're just going to cross that out. I go through, 2 over 4, that's the same as 1/2. We already did that, cross that out. 3/3, cross that out, cross that out. And so you just go through and you eliminate the ones that are repeats as you go. But I have a way of listing all of them, and I have a way of going through and systematically making sure that I have counted and accounted for every single different kind of fraction that we can think of, where the denominator is not equal to 0. Because we have this systematic process, we can say that it has the cardinal number Eliphalet. And I want to just briefly talk about why we have to zigzag as opposed to just going through the list horizontally and looping back. So you don't have to write this part down, but let's suppose that we wanted to approach it from a different perspective. Maybe I want to just start with all of the ones that have a numerator of 1. If I go in this direction and I want to just systematically do every single fraction that has 1 as a numerator and hopefully loop back around, I'll never be able to loop back around because I'll never hit the end of it. So this doesn't work. I'll get stuck here, and I'll never get a chance to hit all of those other fractions. Similarly, if we tried to do it going down, if we tried to count these by going down, I would get lost in all of these that have the denominator of 1, and I would never be able to loop back around or finish this column. So instead, this is really a pretty clever way of counting the set of rational numbers. How cool is that, right? Okay. So, wrap this up. We can say that the set of rationals and the set of rational numbers we abbreviate with a capital Q with this double bar here. The set of rationals is countable. And because it's countable, we can place it into a 1-to-1 correspondence. We can place it into a 1-to-1 correspondence with the set of natural numbers, which we abbreviate as this capital N with the double bar. And then let's just kind of nail down what it means to be countable. We can say that a set is countable if it's finite. Finite meaning it does not go on forever. For example, this is a finite set. It only has 3 elements. It does not continue. So a set is countable if it's finite or if its cardinal number is Eliphalet. And we're going to do We're going to do the rest of this in class together. Okay. Thank you so much. Until next time, have a wonderful day. Bye.